let's consider one more example on collisions. And what we have here is this bullet that is moving towards this mass, which has a mass of 3 kilograms. The bullet itself weighs 10 kilograms and it's moving with a velocity of 300 meters per second. This bullet hits the block and lodges itself inside the block, and the whole thing, because of that, gains a velocity, and it rises up to a height h from its initial position. So the question is, what is going to be the height by which this whole bullet block combination is raised up? Now it's inelastic collision, because we can see that the bullet and the block combine together, and whenever we have this kind of phenomena, then for sure there is inelastic collision. But there is one thing for sure which we can rely on, and that is conservation of momentum. So if the bullet is moving at 300 meters per second, then if we multiply by the mass, which is 0.01 kilograms, so that gives us 3 kilograms meters per second. And this is what? This is the initial momentum of the system. Just after the bullet lodges itself inside the block starts to move forward in the x direction. So what is the velocity of this new block bullet system? Well, this new block bullet system should have the same momenta as the momentum of the bullet, because the momentum should remain conserved just after the collision. Just after the collision there is no force acting, but as the block starts moving, then the tension starts acting and forces starts to come in play. So we really can't say that momentum remains conserved for this part of the journey of the block bullet system. Right here, just after the collision, the momentum is conserved. So what is PF? Let's say the whole system gains a velocity v at the end. So 3.01 is the mass of the total thing, multiplied by v is the final momentum. Now these two should be same. So that gives us, we can sort of ignore 0.01 in comparison to 3, because 3 is certainly much bigger than 0.01. So we can say 3v equals 3, and that gives us v equals 1 meters per second. Okay, so we are now in a situation when this system has started to move with a velocity 1 meters per second. It has a mass of 3.01, but let's say it has a mass of 3 kilogram. Now it's just a problem of energy conservation, because from here to here, sorry for the bad drawing, but let's assume looks something like this. From here to here, what is happening is that this guy, which has a kinetic energy, gives all its energy and transfer let me rephrase. This guy here is kinetic energy, and all of this energy is transferred to potential energy, because it raises in height and it goes up to a maximum height where all the kinetic energy is lost, and all the kinetic energy has converted to the potential energy. And this h is the representation of how much how much is the potential energy of the block with respect to its initial position. Okay, so what is the initial kinetic energy of this block system? We can forget about the collision part now. All that remains with us is this new information now. So what is going to be the kinetic energy of the block bullet system? Is going to be half mv squared, which is 1.5. okay. Also, if it is rising up by a height mgh, the final, let's say this is E initial after collision, E final is going to be mgh, where m is 3 multiplied by, let's say, g is 10, and h we have to find. So E initial should be same as E final. We are not really losing energy in this process. We certainly can see there is a change in momentum. Momentum has changed here, because right here it has momentum in the x direction, but here momentum is 0. And why this is happening? Well, this is happening simply because there is a tension acting on this. The tension is acting. Here also is tension acting, but you see momentum is in this direction. So if you have a momentum in this direction and you apply a force like that, then you're not really changing the momentum in this direction, because these two are perpendicular. But if you have a momentum in this direction and you apply a force like this, then some component of F is going to change the P, and which is what is happening here. Some component of T is changing the momentum, but not here when T is perpendicular to the momentum. Alright, coming back to the energy conservation. So we can write 30H equals 1.5, and H turns out to be 1.5 over 30, which I believe will be 0.05 meters. Okay, and we will all talk more examples, but in the next lecture we will talk about the dot product, which we have been delaying for so long.